Hello friends, welcome back to my YouTube channel. Today I will continue my discussion on high pressure vessels, and the topic for today's discussion is stress distribution in the vessel wall. Since high pressure vessels are thick walled pressure vessels, stresses vary considerably with the wall thickness. They are distributed along the wall thickness. And today we are going to see, or we are going to know, how these stresses are distributed. There are three types of stresses. You have axial stress, you have radial stress, and the third one is circumferential or tangential stress. Hello friends, welcome back to my YouTube channel. Today I will continue my discussion on high pressure vessels. And the topic for today's discussion is stress distribution in the vessel wall. Since high pressure vessels are thick walled pressure vessels, stresses vary considerably with the wall thickness. They are distributed along the wall thickness. And today we are going to see, or we are going to know, how these stresses are distributed. There are three types of stresses. You have axial stress, you have radial stress, and the third one is circumferential or tangential stress. If you look at another cylinder, a horizontal cylinder like this, then the three directions will be represented in this way. You have radial direction, then you have axial direction, and then you have the circumferential direction or the tangential direction. In radial direction, you have sigma r, the radial stress. In axial direction, you have sigma e, the axial stress. And in the tangential or circumferential direction, you have sigma c, that is the circumferential stress or the tangential stress. Okay. So the three stresses, equations for these three stresses, let me tell you. Axial stress is given by this equation: sigma A is equal to pi di square minus po do square divided by do square minus di square. Then radial stress, it is given by this equation: sigma r is equal to do square di square upon d square into pi minus p naught divided by do square minus di square minus pi di square minus po do square divided by do square minus di square. And the circumferential stress is given by this equation: sigma c is equal to do square into di square upon d square into pi minus p naught divided by do square minus di square plus pi di square minus po do square divided by do square minus di square. In these equations, do represents the outer diameter of the vessel, di represents its inner diameter, pi is the internal pressure, and po is the external pressure, and d is any diameter along the vessel wall thickness. Okay, so with these equations, now let us see how they will change with the vessel wall thickness. And to start with, we will look at axial stress at the inner surface. By inner surface, let me tell you what I mean. So if you are looking at the vessel from the top, so you have the internal diameter, and then you have the outer diameter. This is the outer diameter, do. Okay, so inner surface, by inner surface, we mean this surface. So first we will understand what will be the axial stress at this inner surface. So let us understand it. So we will begin with the equation for axial stress. Axial stress is given by this equation: sigma A is equal to pi di square minus po do square divided by do square minus di square. For high pressure vessels, where the internal pressure is very high, they are mostly subjected to internal pressure. The meaning is, for these vessels, external pressure is almost zero. That is, P0 is zero in this equation. At the inner surface, that means we are talking about di, that is when d is equal to di. But in the equation for axial stress, there is no d. So there is no any effect of using this relation. So at the inner surface, by that we mean at the inner diameter. So sigma AI, that is axial stress at the inner surfaces, will be equal to pi di square minus PO is 0, because for high pressure vessels, external pressure is 0. So pi di square minus 0 into do square divided by do square minus di square. That is, sigma AI is equal to pi di square upon do square minus di square. And in the next step, what I will do, I will take di square common from numerator and the denominator. And if I do that, we will be getting this pi into di square upon di square, and the whole thing divided by do square minus di square upon di square. Okay, so that gives us sigma AI as pi upon do square upon di square minus 1. And if I use small k to represent do upon di, sigma AI will then be pi upon k square minus 1. So this is the axial stress, value of axial stress at the inner surface, at the inner diameter. Now let us see what is the equation for axial stress at the outer surface. So axial stress, we know it is sigma A is equal to pi di square minus PO do square upon do square minus di square. For high pressure vessels are mostly subjected to internal pressure only, that is P0 is 0, and at the outer surface D is equal to du. So with this equation for axial stress becomes sigma A0 is equal to pi di square minus 0, because P0 is 0, 0 into do square upon do square minus di square. That is, sigma AO is equal to pi di square upon do square minus di square, and that is sigma AO is equal to pi di square upon di square, do square upon di square minus di square upon di square. Taking di square common, you get sigma AO is equal to pi upon do square upon di square minus 1. And if you use k for do upon di, you get sigma AO is equal to pi upon k square minus 1. That means as far as axial stress is concerned, its value at the inner surface, that is sigma AI, is same as its value at the outer surface, that is sigma AI is equal to sigma AO. Okay, now let us look at the radial stress. First we'll know its value at the inner surface. So radial stress is given by this equation, sigma R is equal to do square di square upon d square into pi minus p naught upon do square minus di square minus pi di square minus po do square upon do square minus di square. So for high pressure vessels, again high pressure vessels are mostly subjected to internal pressure. That means the external pressure is 0, P0 is 0. At the inner surface, you have D is equal to Di. So if you use this information in equation for sigma R, you get sigma Ri, that is sigma R at inner surface, is equal to do square into di square upon di square. Now D is replaced with Di into Pi minus PO. PO is 0. So Pi minus 0 divided by do square minus di square minus Pi di square, again minus PO is 0, so minus 0 into do square divided by do square minus di square. So if you simplify it, sigma Ri will be equal to do square, because di square gets cancelled, into Pi minus 0 is Pi divided by do square minus di square minus 0 into do square is 0, so it would be Pi di square upon do square minus di square. So in the next step, what can be done? You can take pi upon do square minus di square as a common term, and in the bracket you are left with do square minus di square. So that is sigma Ri is equal to Pi because dO square minus di square and dO square minus di square gets cancelled, and you are left with sigma Ri is equal to Pi. And if sign convention is used, since radial stress is compressive, sigma Ri will be equal to minus Pi, that is equal to the internal pressure, and it will act in opposite direction of the internal pressure. Okay. Now let us look at, okay, with the sign convention you have sigma Ri is equal to minus Pi, as I said over here. Then look at the radial stress at the outer surface. So we'll start again with the radial stress equation. Sigma R is equal to dO square di square upon d square into Pi minus P naught upon dO square minus di square minus Pi di square minus Po dO square upon dO square minus di square. High pressure vessels are mostly subjected to internal pressure, that is Po is 0, and at the outer surface you have D is equal to dO. So if you use these values in this equation, you get sigma Ro is equal to dO square into di square upon dO square. D is replaced with dO. P minus Po is 0, so Pi minus 0 divided by dO square minus di square minus Pi di square minus P0 is 0 into dO square upon dO square minus di square. So dO square will get cancelled, and you are left with sigma Ro is equal to di square. Pi minus 0 is Pi upon dO square minus di square, and this is 0, so this will be Pi di square upon dO square minus di square, that is sigma Ro is equal to Pi upon dO square minus di square into di square minus di square, and di square minus di square is 0, therefore sigma R0 is 0. That means the radial stress at the outer surface is 0. Radial stress at the outer surface is 0. So that ends our discussion on radial stress. Now let us look at the circumferential stress. So first we will know its value at the inner surface. Circumferential stress at the inner surface. So circumferential stress, it is given by this equation. Sigma C is equal to dO square di square upon d square into Pi minus P naught upon dO square minus di square plus di square Pi di square minus Po dO square upon dO square minus di square. High pressure vessels, these are mostly subjected to internal pressure only. That means the external pressure, that is Po is 0 at the inner surface. D is equal to Di. We will use these values in this equation. So sigma Ci is equal to dO square di square. D is replaced with Di, so Di square. Pi minus 0, P0 is 0. dO square minus di square plus Pi di square minus P0 is 0, so 0 into dO square divided by dO square minus di square. So now di square will get cancelled, and you are left with sigma Ci is equal to dO square into Pi upon dO square minus di square, and here this is 0, so it will be Pi di square upon dO square minus di square, that is sigma Ci is equal to dO square Pi plus Pi di square upon dO square minus di square, and in the next step you can take Pi common, so it will be dO square plus di square upon dO square minus di square, and if you take di square common from numerator and denominator, you have sigma Ci is equal to Pi dO square upon di square plus 1 dO square upon di square minus 1, and that is sigma Ci is equal to Pi k square plus 1 divided by k square minus 1, because dO upon di is denoted by k, we are denoting it by k. That's why sigma Ci will be equal to Pi into k square plus 1 divided by k square minus 1. Now let us look at the circumferential stress at the outer surface. So circumferential stress, again it is given by this equation. Sigma C is equal to dO square di square upon d square into Pi minus P naught divided by dO square minus di square plus Pi di square minus Po dO square divided by dO square minus di square. High pressure vessels, they are mostly subjected to internal pressures only. That means the external pressure, that is P0 is 0. So at the outer surface you have D is equal to dO. Using this in the equation for sigma C, you get sigma CO. Now it will be sigma CO. Just a minute. Sigma CO is equal to dO square, di square upon dO square. We have replaced d with dO square. Pi minus 0, P0 is 0, dO square minus di square, plus pi di square minus P0 is 0. So 0 into dO square divided by dO square minus di square. Therefore, sigma Ci will be dO square, dO square will get cancelled. You are left with sigma Ci is equal to di square into pi upon dO square minus di square plus pi di square divided by dO square minus di square. That means sigma CO will be equal to di square pi plus pi di square upon dO square minus di square. So pi di square plus pi di square is 2 times of pi into 2 times of di square divided by dO square minus di square. And now if you take di square common, you get sigma Ci is equal to, sigma CO is equal to 2 pi into 1 upon dO square upon di square minus 1, and that gives us sigma CO as 2 pi divided by k square minus 1, because dO upon di is k. So in this way you get the equation for circumferential stress at the outer surface, sigma CO. Okay, now let us collect equations of all the stresses. So we will less the stress, and then we will know what is the equation at the inner surface and then at the outer surface. For axial stress at the inner surface, it is sigma AI is equal to pi upon k square minus 1. At the outer surface, it is sigma AO is equal to pi upon k square minus 1. So it is constant. It is not changing with thickness. Then radial stress at the inner surface, sigma Ri is equal to pi, the internal pressure, and with sign convention, it will be sigma Ri is equal to minus pi, because radial stress is compressive. At the outer surface, sigma Ro is 0. Radial stress at the outer surface is 0. Then circumferential stress at the inner surface, it is sigma Ci is equal to pi into k square plus 1 upon k square minus 1. And at the outer surface, sigma CO is equal to 2 pi upon k square minus 1. So at the end, you can now easily see how the value of this stresses changes from inner surface to the outer surface. So that was the objective for today's discussion, how stresses are distributed along the thickness of the vessel wall. So with this, I end my discussion for this video. I hope you have understood the concept. If you have any doubt or any questions regarding this, you please mention them in the comments. So with this, I end my discussion for this video. Thanks for watching my video. Do subscribe to my channel. Tell your friends to subscribe to it. And if you have any doubts or comments on this video, you please mention them in the comment section. Have a nice day and hope to see you soon in my next video.